This last section of aircraft performance will focus on Class A performance, which, for the purposes of the exam, is based upon the medium-range jet. The specimen aeroplane used is the Boeing 737-400 series. Just to remind you, Class A aeroplanes are defined as being any multi-engine jet, or any multi-engine turbopropeller aeroplane whose mass is 5,701 kilograms or more, or has 10 seats or more. Because of the high passenger capacity and high speed of these aeroplanes, they must have the highest safety standards. You may remember that these safety standards are enforced in two ways. Firstly, by their certification requirements, which are laid down in the CS25, and secondly, by the operational requirements, which are laid down in JAROPS 1. The operational requirements have one unique detail regarding Class A aeroplanes that is actually very different when comparing to Class B aeroplanes. This difference is that the requirements state that for Class A aeroplanes, engine failure must be considered for all stages of flight, whereas for Class B multi-engine aeroplanes, engine failure was not assumed below 300 feet. Assuming engine failure for Class A aeroplanes adds an extra dimension to understanding and assessing the aeroplane's performance. Because of this, a lot of new terms and concepts will be introduced which you will need to become very familiar with before a full appreciation can be made of Class A aeroplane performance. However, before we detail these new terms and concepts, let's examine what the operational requirements are. JAROPS 1 states that an operator must ensure the takeoff mass does not exceed the maximum takeoff mass as published in the aeroplane flight manual. When calculating the maximum takeoff mass, the accelerate stop distance must not exceed the accelerate stop distance available. The takeoff distance must not exceed the takeoff distance available. And lastly, that the takeoff run must not exceed the takeoff run available. Compliance must use a single V1, which we shall understand later, and must take account of the aerodrome conditions. So far in aircraft performance, you have come across a few specific speeds which have been termed V-speeds. For example, VR, which is the speed for rotation, VLOF, which is the lift-off speed, and VREF, which is the landing reference speed. With Class A aeroplanes, there are many more V-speeds, and a few of them are very crucial to the everyday flying of Class A aeroplanes. CAP 698 actually lists and defines the majority of these speeds on page 2 and 3 of Section 4. Section 4 being the section of sample performance data for the medium-range jet 737. The first of these V-speeds to discuss is V1. This is by far the most important speed in the takeoff for Class A aeroplanes. V1 is called the decision speed. It is so called because V1 determines the outcome of a critical decision that must be made following an engine failure or other major systems failure. V1 is defined as being the maximum speed at which the pilot must take the first action in order to stop the aeroplane within the remaining accelerate stop distance. But V1 is also the minimum speed following engine failure that the pilot is able to continue the takeoff within the remaining takeoff distance. If the engine were to fail before V1, then the decision would be to abort the takeoff. The reason is because with only one engine operating, there would be insufficient takeoff distance left to accelerate the aeroplane to the screen height. If the engine were to fail after V1, the decision is to continue the takeoff. The reason is because the aeroplane is traveling too fast to be able to stop within the remaining accelerate stop distance available. In order to understand how V1 is derived, we need to consider a graph. This graph plots the takeoff distance required and the accelerate stop distance required based upon a varying engine failure speed. Firstly, let's consider the accelerate stop distance required. If the engine were to fail at a slow speed, then the distance to accelerate to and then stop from the engine failure speed would be very short. However, if the failure were to occur at a very high speed, then the total distance to accelerate to and then stop from that very high speed would be very long. Now let's explain the takeoff distance required curve. If the engine failure were to occur at a slow speed, then the distance required to complete the takeoff would be very large, since the majority of the takeoff will be carried out with only one engine. However, if the engine were to fail at a high speed, the takeoff distance required would be much shorter, since the majority of the takeoff has been completed with two engines.
Having understood what each of the lines in this graph represents, in Part 2 of Class A Takeoff, this graph will be further explained and then used to help select the position of V1.